So in our discussion post, you talked about what the word momentum means to you and some typical uses of the word in everyday English. Also, your personal definition of momentum. When have you heard it used and what do you mean? What does it mean to you? Perhaps when a coach is talking about having good momentum in a game, or when somebody's moving really fast, you say they have a lot of momentum. So let's go into our physics definition of momentum. Momentum is a vector quantity. The quantity is going to be mass, which is a scalar, times velocity, where velocity is our vector. So we'll want to be looking at the direction of the velocity of an object to define the direction of momentum. The symbol for momentum is a lowercase p, and the arrow on top of it will remind us that it's a vector. Why momentum is symbol P is kind of hard to explain. I usually say that it's because it used to be called momentum, but then we lost the P and it became silent, and then we just dropped it all together. That, of course, is a lie. I really have no idea why it is symbol P. Probably because the other symbols are already taken. So our mass for momentum is going to be measured in kilograms, and our velocity is going to be measured in meters per second. Together, that'll give us our units for momentum, kilogram meters per second. Kilograms. There's no other way to simplify this. Unlike energy, we don't redefine it as joules. So if you want to change momentum, you are going to have to apply an impulse to the object that has momentum. So if you thought about someone moving towards you really quickly and you wanted to stop them, you're going to apply an impulse to them. So impulse is also a vector quantity because it has a direction. You're either going to push something backwards or forwards, continuing its motion or stopping its motion. To apply an impulse, you're going to take a force, which is a vector quantity, and you're going to multiply it by the time in which you apply that force. So impulse is J, it's a vector, and it equals force, which is a vector, times time. Impulse units are newtons for force times seconds. Now, if you think about what's a newton, right? What is inside a newton? A newton is a force. A force is a mass times an acceleration. So this is really a mass in kilograms times an acceleration in meters per second squared, multiplied again by seconds, thus simplifying to kilograms, kilogram meters per second. The same units as momentum above. This leads us to understand that an impulse will change an object's momentum. So impulse is also a change in momentum. We write that using the formula impulse J will change momentum, delta P. Remember that a delta is a final quantity minus an initial quantity. You can really write this out in more details by expanding what J is and what P is. So you can write J as force times time, and you can write P as mv final minus mv initial. This is the most expanded way that you can write your impulse momentum formula. Now, let's go back to what Newton's second law is. Remember Newton's second law? F equals ma, where force is a vector and so is A. If you redefine A by writing out that it's a change in velocity over time, you can then multiply time to the other side. Time times force equals m v final minus v initial. You can put the m into the parentheses, so time, force, mv final minus mv initial. Then you realize that force times time is the impulse, and mv is p final, and mv initial is p initial. So really, when we're talking about impulse changing momentum, we're just applying Newton's second law in a different way, given the quantities that we have. So an external force can make an object accelerate. An external force can apply an impulse and have an object change momentum. If you want to change a momentum more significantly, you can either increase the force or you can increase the time. Let me show you some examples of that.
This is also why baseball players are taught to swing through the ball rather than stopping the swing upon impact. because if contact is maintained between the bat and the ball for as long as possible, the maximum possible force will be imparted upon the ball.
So in that example with the bat hitting the ball and giving it momentum, you want a large impulse. You would like force to be large and delta t to be large so that your momentum change in p is large, giving your ball a large final velocity after leaving the bat. Now there are some cases where you're not in control of what delta p is. If you drop something, let's say, then it's going to gain a velocity before it hits the ground. And as it impacts with the ground, that mv quantity will turn into 0.
And so let's look at two spheres that are being dropped on a table. Let's imagine that they both fall with the same velocity and they both have the same mass. So watch what happens to the first one and then the second one. And so a good question might be, which has experienced the most dramatic change in momentum? That's kind of a trick question. Since they both have the same mass and the same velocity, and at the end they're at rest, they've experienced the same change in momentum. Therefore, their impulse is the same. And so what's different in these two spheres as they fall to the table? Well, it's the time over which they interact with the table itself. The one on the right is really slowing down over a longer period of time. And that means it's applying less force to that table.
There's another example of this that will come into mind when you think about summertime activities with friends. When you're playing water balloon toss with your partner, you're increasing momentum every time you toss. You're giving the ball an initial velocity. As your friend catches the ball, they are in charge of taking that initial momentum, mass times velocity, and bringing it to rest, creating a final momentum of 0. So there's a delta p happening here. After your friend catches the ball, you back up, increasing the distance. Your friend will now have to throw the ball with more momentum, more initial velocity in order to make it to you. But you still have to bring the ball to rest. The delta p is now more than it was previously, and each time you back up, you'll increase your delta p. Delta p is the same as impulse, j. Notice that delta p is not something you control. You have to bring the ball to rest, and your friend is in charge of the initial momentum. So the amount of impulse that you need to give the ball is determined, the balloon. And you know that a large force on the balloon is going to pop it. So you can pick which way you want to apply the impulse. If you extend the time, making t larger, you can manage to make f smaller. So you'll take your arms and you'll follow the balloon downward, thus making this arcing motion and increasing the contact time you have with the balloon. So that even though the impulse needs to be some number out of your control, you break it up to have a large t, thus cradling the balloon, and having a smaller f. This way, your balloon doesn't pop. But some things don't always go as planned, and sometimes it will pop. Let's work through some change in momentum example problems. Here's our pitcher. On this side over here is our batter, and they're going to hit the ball backwards, right back out towards the pitcher. So our definitions are up above if we need them. We can reference them at any time. Let's take the information from the problem and write it down. So you have a 0.149 kilogram baseball. That's going to be our mass. It's thrown by the pitcher to the right. The right is the positive direction. So V initial is going to be a positive number. It's moving at 26 meters per second. The bat is going to contact our ball with 7,750 newtons of force, F. Now think about which way the batter is going to hit the ball. The batter is going to hit the ball back in this direction, F. So the force is going to be to the left, which will be a negative number. Then they give us the time in which the ball and the bat are touching. Let's go ahead and answer these questions about the scenario. The initial momentum, P, of the baseball is going to be the mass times the velocity of the baseball. We get 3.874 kilograms meters per second. There's a positive number as a vector, and it means to the right. Now let's get the impulse, J, applied by the bat. J is force, times time. We have the force, 7,750, and the time. Now this impulse is applied to the left, so let's put a negative sign on it showing left. Our impulse comes out to be negative 9.7 Newton seconds. Remember, the negative is showing us that the bat is hitting the ball to the left, and we call the left negative. Okie dokie, let's combine these things together to get the baseball's speed after being struck. So we know that impulse will change momentum. So we'll have J equals P final minus P initial. Now we already know what P initial is and what J is. So impulse is negative 9.7. And then P final is unknown. And P initial is 3.874. So first we can find the P final value of the ball. So when we solve for P final, we get negative 5.83. The negative just tells us that the ball is moving to the left. We can set this equal to the mass times the ball's speed, v. That v will come out as a negative number, which will give us a velocity that is to the left. So we find v equals negative 39 meters per second. That makes sense, as our ball is going backwards after being hit by the bat.